Hello, welcome back to another video in my Boundless 2D game engine video series here on the Lötwig Fusel channel. Now in the last video we basically implemented interfaces and inversion of control registrations. So basically I have defined an interface inside of my API project that is of course set it up not correctly, and we basically defined an interface with a virtual destructor and a say hello function, and then inside of a module we defined the implementation of the interface called dummy for the iDummy interface, and we implemented it depending on what kind of app we have, that we have a message box or a cout. Currently this doesn't work because all our newer configuration is working because we have not implemented our win main currently, but this is something that we're going to do in future videos when we're going to start with the system initialization in general. Now in today's video series we're still on the inversion of control and module theme, so what we are doing with that. And then we're going to probably have a bit of bootstrap that is in general about setup, with setup of SPD log, setup of the engine and stuff. Currently you can see you can create an IoC registration in the registrations class. You can see that we are registering an iDummy interface, and for that iDummy interface we are registering the dummy implementation. Currently we are only registering one implementation. Of course we could add multiple of these. I think we didn't even tested that later on the last video, but of course it also works, right? Now we have made a few things, we haven't made a few things. We actually have not implemented this as a singleton, which is something that I want to do now. Currently you can see that the IoC registrations, do we even have code in the CPP? No, we don't even have, it's completely header only. But currently you can see that this is all public and this is all inside of the header, and what we want to now do is basically we want to make this a singleton. So let's actually make the constructor private in here. So IoC registrations, let's make this one a default but private constructor. We might also want to have a, that's not what I wanted to have, we might also want to have the copy and the move constructor as a default implementation there. I mean, actually, if we are having a singleton, we can also delete them as well. Why can we delete them? Because I mean, it's a singleton. We're only gonna have one instance of it. And this instance, of course, needs some storage. Now, we could do this in multiple ways. We have a CPP file, so we could just basically implement it inside of the CPP file. However, I think we're going to make it both. We're going to make it a CPP file in here. So we're going to have a static, oh my goodness, I'm too bad to type. IoC registrations get instance. Oh, let's just call this one get, so that we have an option to get this. And then inside of here, static IoC registrations instance, and then we can return the instance. Now we have hybrid no, it's not hybrid initialization, it's actually more or less completely static initialization. We have it statically set it up on the inside of here, living inside of that function. And it's then going to be retrieved and you call the function. However, it is kind of still dynamic initialization because we have no constructor that gets called, and it kind of gets dynamically constructed and initialized every time we call register. Now this should basically render that code worthless. Yeah, we can no longer do it like that. What we need to do is we need to get ourselves the container instead of directly referencing it from the main. We need to call the get function, and then we can operate with the get function. That's the whole idea, right? Registrations shall work and lookup shall work like that over one single instance of the container. That's the idea. Now what we want to do now is we want to build a IoC stack based on these registration that's going to keep track of the instances that have been initialized. So what I'm going to do is I'm going to add a new element here. I'm going to select the header file, and what we're going to create ourselves is an IoC stack. So IoC stack, if we reference our PowerPoint slide, we now have the registrations and a way of giving me kind of the descriptor. And the IoC stack basically manages these descriptors. So the IoC stack basically have a reference to the descriptors. Actually, we're going to have a copy of these. It's going to be sufficient. And then inside of that, we're also going to have an instance, so that we're only going to have one instance of each descriptor. So let's create an IoC stack. The IoC stack is actually a bit more involved than what we had previously. So let's make a namespace BL2D, and let's make a class IoC stack. Now, how do we going to implement an IoC stack? So first of all, we need a bit of internal structures. So I'm going to have a struct called entry. We could make this private maybe. Let's make this private and call it list entry. We're probably also going to have maybe something that's publicly exposed. Maybe not. Let's keep it until we have something that's exposed. And then let's include our IoC registration. So we're going to have BL2D / common IoC registration and registrations. That's what we need for that. And inside of here, we have a registration, which is going to be the descriptor. So we have the descriptor of the entry. And what we're also going to have is we're going to have a void pointer, and this is going to be called the instance. So this is going to be a null pointer. That's basically what we have. We have a descriptor and the instance, and this is the entry. Now, I think the registration is not bound to an API or anything else, so we might also want to have these stored in here. I'm not quite sure if we want to, but we might. But actually, I don't think that we need them, because basically, yeah, this is not list entry. Let's call this one stack element, because this is basically a stack element. And then we're going to have an IoC, and then we... Okay. Now, before I'm going to get too complicated, I want to explain you what I want to do. So in general, we have the IoC stack, right? You can see that inside of the PowerPoint slide, I have defined the stack here inside of the IoC stack, which has a descriptor and an instance attached. This is basically what we have just now created. And what this allows us is to build up a kind of like list. We can start with one element, and then we have another one, and we kind of like append them all to the list until we get a point where the list is finished, everything is operating, and at some point we are destructing the list in the reverse order. And for this is sufficient, right? We have the descriptors with the CTOR and the DTOR and the size, so the stack element is 100% sufficient to create and destroy objects in order. However, we need to know when we want to create elements, and when we want to actually create objects, and when we just want to return the instance in a certain way. And for that, I actually want to define a second structure, a acceleration structure. And the acceleration structure is basically going to be an unordered map of a combination of a name and the API to the actual implementation on the stack. And if we can't find it in the accelerator, we create a new one in the stack and also bring it in the accelerator and kind of like point to the stack. This is kind of like the idea that I want to follow, because if we would put everything in the stack, we always would need to linearly search the stack, and this is not what we want. So what we now need to define is actually we need to define a shared key. Currently, if we would take a look at the registrations, you can see that registration works by the type index and then a string, so a two-dimensional nested unordered map. We could just basically represent this as well in the accelerator, but we could also do it differently. I mean, we're just going to put it in like that. Maybe That's a good question. I don't think that I think we need that order in here, because we are kind of like doing this in a true lookup. Maybe we're just going to copy this over to the stack. We could also define a so-called shared key. We could define our own struct based on an API and a string, and then provide our own hashing function. But I think actually this two-layer approach is actually a good idea. So let's maybe make this with type index and unordered map in here, and let's make the IoC stack a bit more simple. So public is going to be our function interface, and private is our members, and what we have is an unordered map, and instead of going to an IoC registrations, I'm actually going to point to a stack element, which is going to be M accelerator. This is going to be the Let's call this one here API to stack. This is the API to stack list or map. And then I promise you that we're gonna have a list in here. And basically what we're gonna have additionally is we're gonna have a list of stack elements. This is my stack. So we have the actual stack, and we have the API to stack pointers. stack pointer API to stack. I think API to stack is sufficient. And that's a general idea. Now this can all be default constructed, so this is actually fine. The only thing that I want to disallow is I don't want to support copy. So not pointer, reference. So let's delete that one. I also don't want to, maybe we want to have move. I'm not quite sure if we can have a default move, but I think it should be, yeah, we can have a default move because we're just using these. So that's actually fine. The same goes for the assignment operator. So let's define them like that. So now this should work. I quickly want to specify that we have a default constructor and then we should be fine. We can't copy, but we can move. And this is sufficient. Now what we need to do is we basically need to define a few operations on the stack. And basically the stack is going to have a few private functions that are actually like modifying the stack. So we're going to have a push and a pop. Actually, I just want to have stack pushes. And I don't think that we even implement them in our own function because the stack already supports these. Whoops. Like that. Because you have a list. I mean, we could... I think there might be even a std stack, right? That we can maybe even use. I think std stack is a thing that we could directly use. Which is a queue. I'm not quite sure how this works. Because we can actually let's actually use the stack here, not a list. And basically the DQ is a list, right? The only thing that not DQ, of course I want to have a stack. Let's actually do a proper stack because we then can basically have the push and pop operations inside of the way that we are doing it. But how do we actually fill the stack? Well, basically we fill the stack in a very graduous way. So in general, what we're going to have is we're going to have a templated function type name t, and this is going to be a t. Yeah, let's call it t reference, and if we can't find it, it's going to throw a t reference get function on the IoC stack, and we can have a const std string view name, which is by default is equal 0, but since it's a string view, we don't want to actually have it like that. So that's kind of like the idea. A string view in here. This is basically the idea of the retrieval interface, how we are going to retrieve something. So a t reference. Now, in general, what this is going to do is I'm going to write a void pointer get function, another get function, which is not possible. Let's call this get ptr for get pointer, and the get pointer is going to have an std type index type. Then we're going to have a std string view name, just by default also like that. And this call is basically gonna I mean, let's make it pointers for now. Pointers, I mean, yeah, we need a way to validate these pointers. Maybe we're gonna later move to a I mean, this is now let's make it a reference. We can do it, let's do it in two ways. Let's make first a pointer, let's call it pointer, and let's call get pointer. And get pointer is type ID of t, of the interface, and then we have the name in here. And this can be get and forward. And later on we're going to return the reference pointer, and in between we can later on put in checks to throw if there's something to do. Check. So that we can throw if something is wrong. Now this get function actually can go into a implementation file, and we might not even need to have it too complicated at all. No, I don't want to rename. Alright, so the get pointer. Alright, so how does that work, that get pointer function? The first thing that we need to do is we need to check if we own it. Actually, what I need to do that I haven't implemented, I need to operate with a parent stack. I told you that I want to be able to support parent stack. And that's how we want to do it. I want to have a parent stack here, null pointer, and void set parent. IoC stack reference stack. And basically what I want to say is parent come on. Yeah, okay, nice. This doesn't work, but like that. And maybe we also want to have a way of registering that get parent. We're gonna return the stack like that. Dereferenced. Parent like that. So that we can also return the parent if we have one. I mean, this is also an answer function, so maybe we should do additional checkings there as well. But for now, I think these are fine. Inline. I mean, this is perfectly example for a non-safe C++ code, but yeah. So how does retrieval work? So we're gonna have a void pointer instance. It's just gonna be equal to null pointer. And at some point, if not instance and parent, or mparent, if we have a parent, return parent, mparent, get pointer, no, get pointer, not parent, pointer, type name, or in that case, return instance. So this is kind of like, if not found, then request to parent. So if it's not found the current one, we are sending it to the parent. Now, the only thing that's now a bit of a concern is actually we need to send the request to the parent first. Because first we're gonna retrieve things on an application level and then on a sub level. Because if it's not exists in the application level, we send it to the sub level. Okay, so actually we're gonna do it differently. Instance equal parent. If we have a parent, then we're gonna get the pointer from the parent. Else we're gonna set it to null pointer. Then we're going to return the instance. If not instance, so if the parent didn't find it, then we're going to search it locally. So first on parent, then local. So how do we do it locally? So first we need to ask our accelerator API to stack. This is what we want to do. So auto it bin, so the bin that we want to find, or let's call it let's call it bin for the kind of like bin where it's into the API bin. So we're gonna try to find the type, and if it bin not equal end, then we have an auto reference bin, and the bin is the API to actually no, it's the it bin second. This is now the next vector. This is the bin where we are actually now into. And then I have the auto instance. It's not an instance, it's actually the, let's call it element, or it element, the element of the iterator. And this is basically a search in the bin for the name, which needs to be marshaled as an std string in here. And if it element not equal bin end, so if we actually have an element that's inside of that, we can say that the instance is equal to the it element second dot what? It element second. I think it's a pointer, right? It element second, and then it's the instance that we have here. Because if we have it inside of that list, it's good. Now, if we don't find these, so if we are currently here, so first on parent, then local, so find instance. So if we are finding an instance, if this fails, create instance. So first of all, we consider the parent. If the parent fails, we are trying to find an already existing instance on our stack. And if that fails, we're going to go inside of the create instance. So if not instance, so if the instance is still not in existence, now I want to put it in my stack. And now what I'm going to basically name that is I want to name it push. So stack element pointer push. Now we want to push something on the stack. What do we want to push on the stack? We want to push something with a type index and std string view name in here. And maybe actually stack is not even correct. Actually, I have changed my mind again. I want to have a list. Why do I want to have a list? Well, because I always want to have access to all elements in here. And I think the stack is does the stack, like, okay, before I'm going to change my mind too much, how does the stack operate? Can I push an element to the stack? I have no idea if I can. Where is my push? Collect, or what? Why they are doing? It's always void. It's copying that. It's copying or it's moving it. And this is something that is a problem for me. Now we're gonna have a list. We're gonna have a list because I later on need to reference it. But if I have it on the stack, can I peek? Does the stack relocate? That's the big problem. That's a big thing, right? Does this std stack relocate its element, or are they in place? How can I assert that the stack works? Back push pop, so that's not actually in there. I think the std list container allocator aware container. I'm not quite sure. I want to have a container that's not reallocating its element. I think the list, or at least if I would think that the list would not relocate because it basically has like a proxy per element. But it's not directly in here. Implemented as a whatever. Ending, removing elements. Oh, I think we're gonna try it out. Right, later on, I mean, we don't have fast random access, so that's why I would think that the list is maybe the proper one. We're gonna try it out. If it is a problem, we need to switch containers. The general idea of a linked list is actually that you have a pointer of an element inside of an element, or that the actual element is allocated within the list. And the thing is, like, you have like one list element which has like the next previous pointer and then the data on it. And this most of the time is like done with a pool allocator, and you don't really need to reallocate, like if with an std vector, right? If you resize an std vector, it gets a near memory address. Every element has a near memory address, and that's what I want to prevent. But I hope that this is correct. So if we're not in here, I'm basically going to say auto pointer. Yeah, that's a good question. How did the interface look like? Push the stack element pointer type index. Yeah. So element equals auto pointer element equals push for type and name. That's the idea. Why did I forgot to add type in here? Type. There we go. Now it's there. Type. So the general idea of push is that we're pushing a new element in here, and if this element is sufficient, so if we can actually gain something out of that, we now have an element, and we can set that the instance is equal to not else the elements instance. That's the idea, right? Create instance. Now, how do we do a push operation? Push operation is actually quite simple. First of all, we need to query for a registration. So auto pointer descriptor, or not descriptor, let's actually make it, yeah, let's make it a descriptor, and this descriptor is equal to BL2D IoC registrations get lookup. And now the problem is that the lookup function does require a template parameter, which is something that we have overseen, that this should work without one, actually. But that is like a big problem that I have done. API and interface, type ID, API, size of instance. So the set function takes a name, a type index of the API, and the size of, or size t, size. That's the signature of that function, how it actually should be. And without a template. And then we can move that implementation down in here. And then we have the API in here. And we have the size. It's a bit more straightforward. And then you can see that we are using the wrong calling convention in here. So it's going to be the type ID of the API and the size of the instance. That's the idea, how the call should not now look like. And I think this is the same above here. Did I had the set method? No, I only had the set method here. This is how it should work with set. Oh, interesting. New instance pointer. That needs to go like that. I mean, the set. I didn't need to have to change the set one. I'm actually an idiot. Let's keep it the old way. You don't need to do stuff that you don't need to change, right? We don't want to change stuff that we don't want to change. That can be automatically be done like that. We're just going to write another lookup function. That's I think the better call. We're going to write a lookup function that is not templated. Basically the signature, but instead of only that, an std type index type and a name, and then we can implement this properly. It's basically that code, but in a different way. Come on. Give me an option. Thank you. Now we can paste that code. Instead of the type ID here, we can use the type directly there. And actually we can now ditch all of that code, and then we can return lookup of type ID of t and the name. And this makes things a bit more simpler. And actually, I think there I have gone for the empty name. We can completely remove that and set this one equal to that, and then this code is also a bit more straightforward and way simpler. Yeah, shouldn't change anything, but it should allow us to do a type name lookup here. So now we have a descriptor. So if we have this descriptor and do something, let's have our default null pointer return. And inside of here, basically we need to allocate a new stack element. So if I'm gonna say stack, my stack, and I want to push back. I don't know why it tries to default to push front. We need to construct a stack element. The element is gonna have a... No. We're gonna push back a... No, element. Right. This is the stack element. And the stack element is gonna have a descriptor, which is gonna equal to a copy of our current descriptor that we retrieved, and the instance is gonna be set to null pointer quickly. I don't know, but I think we have a default constructor here. Yeah, we have a default instance, so we can just set the descriptor, and then we can push in the element with std move, so that we move the reference to that. And I think this is not gonna give us something back. So can I have back to get the last element? Yeah, I've pushed back, and then I can get the last element, and I can basically later on return a pointer to the last element, which I hope is gonna be... Maybe we should quickly search this. Std list relocation of elements. Let's see. Move list element to the... What? Element is... come on, let's go to our good old friend ChatGPT. I'm not quite sure. Let me quickly move this away so that I can make this YouTube friendly. I don't know if I still have some confidential information in here. I mean that I don't have any confidential stuff in here, but I might not want to show everything that I was working on. So in C++, can I safely assume that the call std list back that the call can I safely make a pointer from the call to std list back? Yeah, let's ask it like that. No, I mean, but does the pointer stay the same even after many list operations? If I would have implemented it, yes, it would be the same. Yeah, of course it's popped. Okay, I'm fine with that. That's fine. That's fine. That's exactly how I would expect the list to actually work. It's good that it also works like that. So this is in general fine. This is all working fine. Now let's actually continue on. And even after we basically moved them back, we now want to have an element pointer. So let's actually say auto pointer PTR. Yeah, I know it's a bad convention. And now basically want to take that descriptor and fill it. So right, PTR instance equals malloc void pointer. It's also already void. Yeah, malloc of pointer descriptor object size. This is kind of like the idea that we want to do in here. And then I basically want to say descriptor, and then I have the CTOR, the constructor, and I want to feed in the instance so that the instance gets constructed. That's kind of like the idea that happens here. The only thing that I want to now change is actually how the CTOR works. Because now we have the concept of an IoC stack, and I want to reflect the IoC stack in our object constructions. Now basically everything, I do still want to kind of like, let's keep it as is currently. I might want to be able to kind of like inject the stack that objects are currently constructed on, because if an object constructs itself and it needs a reference to a different object, what I want to be able to is in the object constructor take the current stack and then basically say, hey, stack, I also need that object. That's something that we also want, which might allow us, maybe we... We're gonna see. We're gonna see how we can implement that. I don't think that we like. Okay, so right. The thing is, I'm just gonna now assert that this is really the case. It now needs to fulfill that. Now the CTOR is now also gonna get IoC stack references. This is now how the new constructor shall work. The destructor not. I don't think that we needed a destructor, right? The destructor can just destroy the object. It doesn't really matter because the stack is currently in the state of being invalidated, and though it should not perform it. The only thing that we should currently be concerned is the order in which things are put on the stack. Actually, I think we only want to put it on the stack as soon as its dependencies are on the stack, actually. So, the IoC registration, first of all, this is no longer valid. IoC stack register is here. So stack. And basically what we want to do is we want to kind of like pass on the stack to the instance. That's the idea. The CTOR and DTOR like that. And now the only thing inside of the stack that needs to be changed is, should see that this is no longer working, but if I dereference this in here, this works. However, right, you can see this is the element. And basically what I want to do before I put this on the stack, I actually want to first initialize the instance. Element descriptor. I want to first initialize it because this is now maybe doing a recursive call. You can see that currently we just iterated, we have no pending reference, we are inside of here, and the pushback happens here, and as soon as the pushback happens, I can return stack back pointer. That's not fine. And what I also need to do is I also need to go to my API to stack and go to type and name and set this also equal to that, which is basically a stack element or auto pointer is equal to that. Then I can basically say, alright, this is equal to the pointer, and then I return the pointer. So this is kind of like construct or create instance. So we are creating an instance, then we are basically storing the instance. Now basically the idea is, if inside of the constructor I kind of like request some other object to be already existing, the other object that needs to exist before my object is going to be put on the stack first. So later on, when we are rolling back the objects, the object that is kind of like dependent on the other objects is destroyed first, so that all dependents are destroyed before, or all the dependents are destroyed before its dependencies. Of course, this is gonna resolve in an issue if we have a circular dependency. However, circular dependencies is something that is in general a problem and should be avoided. Right? Why do we have circular dependencies we shouldn't have? Like file system and logging would be a problem, right? If file system requires a logging API, but the logging system requires the file system to put on their logs. This could be a potential circular dependencies, but that's something that we're not going to have the problem. Alright, so this is kind of like the idea. This is how push should work, and this is how we use push. And now we just need to kind of like have pop, or in this case, actually, we're not going to have pop. We have get and get pointer that kind of like revolve around the same thing. And now what I also want to have is I want to have a void clear, and void clear shall completely destruct the stack. How is clear going to be implemented? The general idea is very simple. We're going to say while stack is empty, basically not empty. While the stack is not empty, we do something, and at the end we have our API to stack and we clear it. So how do I basically want to roll back my stack? I mean, I could have destructor so that it gets destroyed automatically. However, I didn't know in which order the stack is destroyed. I am asserting on the reverse order, so I definitely want to have it like that. So I basically want to pop off elements from the stack. Pop back is actually implemented in here. How does pop back work? Inline void. Okay, so I need to do it the other way around. Pop back. So auto reference element equals back, and at some point we're gonna pop back, of course, from the stack. Now what I basically can do is I can go to my element, I can go to the descriptor, and I can run the destructor for the element's instance. That's the general idea. And then I can call free on the on the elements instance. And if I call free here, object destroyed successfully. Get an element reference, call the destructor, free the element. That's everything nice and clear. And then we pop and we continue on until we have no elements on the stack. And then we have API to stack, which of course also needs to be cleared so that all of our acceleration stuff is removed. Now we have a stack for kind of like managing the kind of like order in which objects are on the lifetime, and I can continue on. We could actually try to solve dependency problems by doing it basically that way around, but if we would do it that way around, it's actually, I think, bad, because then an object gets called when it's not completely constructed, which is also like undefined and should not happen. So I think this is the way on how we want to do it with the stack. I mean, we did do quite a long time, actually worked too long on these. Should have gone faster. You can see this shall no longer work. We can no longer use the CTOR plainly like that, but what we can do is we can create ourselves an IoC stack. IoC stack here. And what I can basically do is I can say, maybe we can even do this completely, right? Like BL2D IoC or BL2D dummy, iDummy, my dummy. Can we do this as, well, of course we need a stack. BL2D IoC stack. Right, we can have a stack and then we can register. The order is actually, it's not dependent. I don't think that return values were not able to be deduced, right? So we need to have it as an auto reference to my API. And then since it's now a reference, I can say hello. And the general idea is that that piece of code is doing the same thing that we had previously, but better. Now, what is the problem? Overload member function set. Okay. IoC registration set. Name API save. Ah, yeah, because yeah, of course. I undo the changes and it's still in there. Okay, makes sense. Still a problem. IoC dummy, no overload. Oh, of course. Okay. Yeah, of course, now our implementation needs to take a constructor, right? I now need to have a dummy constructor, then can actually take the IoC BL2D common IoC stack. We need to always be able to take an IoC stack. Not void, just dummy. Like that. If I have it, it should work. Because now the implementation defines that. Or not. Cannot convert to void pointer to iDummy pointer. Yeah, because this is a void pointer. And we're gonna make that an auto pointer and cast it to that. That should work. Because they are stored as void pointers. Alright. So this is shall now be initialized. So the stack has no parent, has no stack, has no API. As soon as I call the get function, we fail. And let's actually take a look on what we have. All right, so we called get pointer with a type of iDummy. And basically what we have done is we have called push. Of course, yeah, I can't get back if I then push it on there. I need to push it, then I can get it back, and then I can use these. Okay, yeah, makes sense. Messed up the order while refactoring. This should hopefully now work. Okay, it works. So what we actually have now modified is we have a myDummy, which seems to be legit. Is it legit? Yeah, there we go. Now it's legit. I just need to expand it. And you can also see that the stack itself has been filled. So we have a stack with an element on here. We have an API to stack accelerator that helps us getting the objects multiple times. And if I continue on, the functionality should be still the same, right? We get a hello world. Now, the interesting thing is we can now create as many myDummies as we want. And we're always going to have kind of like the same... the same interface. Now I can just quickly make these as pointers. Yeah, then we can say hello. So pointers are always a bit better to observe where they are. And if I run these, they are going to all be on the same memory location and it's constructed once. So if I take a look at these, you can see it's 3 times the same pointer and the stack is also not modified. And that's the whole idea of this initialization, of this semi-dynamic initialization, right? If I run it like that, before I'm going to get the first instance, the stack is empty. Then on the first call, the instance has been created and allocated. If I now kind of like step over these, they basically just return the same pointer every time. And the stack also shall be deconstructed at some point. We can quickly simulate these, or we could manually. Oh, I think the stack isn't even automatically deconstructing itself currently, because we just had the function, right? We just had the function clear, which is of course not called by default, which is a bad thing. So this is something that should be called on the destructor. So clear should be called here. And if I can call this manually, so I can call clear in here. Not myDummy, it's going to be the stack. The stack is going to be cleared here, and at the point where the stack is cleared, all instances are destroyed. And the pointer shall be invalid. We can actually observe this. If we are continuing on here, the pointers here, they are now invalid because the data where they are pointing to has been destroyed because the stack is destroyed. And this was basically the whole story about instance-based dynamic initialization, right? We have a bunch of singletons, in this case the dummy singleton. And of course, it's always not going to be single. It's not everything is going to be an IoC. We're always going to have just the factories in IoC, and then the factories can create also objects that are not even IoC registered. This is the concept that we are doing here. You can see that the code behind it is very simple. Of course, we could be even more fancier and have like dynamic object generation depending on how we do the calls, and that we have custom arguments that we can give them. But no, this is all too fancy. Our IoC shall be darn simple. You can see, like, it's not a big deal. Like the stack, it's like roughly a bit above 100 lines of code. The registration itself, under 100 of code, and just 20 codes of a bit of a descriptor. So actually, as you can see, the code that we are writing here is very, very simple. And that's the whole idea. I don't want to have too much complicated stuff in that engine here. I want to have something that's understandable. And I want to be able to define modules and interfaces and dynamically link them all together and initialize them as I want. To have it very, very simple. And that's it for today. I'm way too long than what I've actually wanted. Now, thank you for watching. We're going to see us in the next video where we're actually going to go into the architecture of modules. So you're going to try and kind of like make this module dynamically load itself into our exe with so that we don't need to do anything. Okay, we're always going to call like one functions, but like what we are doing here, these are IoC registrations, which if we are taking it serious should be rather in that order. I don't want to always register them manually. This is something that shall be done on a module base. Every module should have a function to initialize itself, and these functions shall be automatically built into each application. And then later on, when we're going to episode 3, we're going to talk about initialization, how we're going to abstract all these initializations away from the actual target application and build a bit of a framework around. And that's it for today. Thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Until next time, bye.